So let's imagine that we're given 5 letters, A, B, C, D, and E, and we're asked how many different ways can we arrange these 5 letters? Well, you can also use A, C, D, E, B, or you can use B, C, D, E, A, or you can use B, D, E, C, A. These are all different ways of arranging the same thing. And these are also an example of permutations. So you might be thinking, what exactly are permutations? And basically, permutations are the number of different ways you can arrange a set of things. So in this case, each time you rearrange A, B, C, D, E, while it still has the same letters, it's rearranged in a different way each time, so they're unique. That's why the way we can express the number of combinations that we can make is 5p5. Now, this notation may look unfamiliar, but it's also referred to as the notation used for permutations. So let's start at the beginning. What exactly are permutations? We've said that they're the arrangement of the same set of things, but more than that, what do we actually know? Well, permutations, they refer to the total number of arrangements, right? So you can think of permutations and what we're going to come to later, combinations, as the total, as a strand of probability. So probability is the total possibilities with a condition over the total possible outcomes. Like, it's a ratio, right? Probability. Permutations isn't a ratio. It just focuses on this strand of the equation in more and more detail. So coming back to this question here. So we've identified that there are 5 letters, and therefore you can arrange them many more different ways. And we've used this formula, but what exactly is this formula made of? Like, we just said 5p5, but that means nothing unless we actually understand where it come from. So basically, 5p5 came from the equation NPR. So NPR is the notation used for permutations, where N is the number of values or like variables used, and R is the number of items that are actually being used to rearrange the thing. So let's simplify that. So there are 5 letters here, so that means N is 5. And we're using all 5 letters to rearrange them, so it's also 5, so that becomes 5p5. So how do we evaluate 5p5? Well, 5p5 is actually where we use 5 factorial. So factorial is when you multiply everything beneath the number itself. So for example, 4 factorial is 4 times 3 times 2 times 1. And 10 factorial is 10 times 9 times 8 times 7, so on and so forth, till times 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120. So that means that there are 120 ways of rearranging this. But you may be asking, how did we suddenly just get to 5 factorial? Well, we can think about this by using a diagram. Diagrams are often really helpful to use because they make us visualize things in a way that we probably can't do in our head just like that. So we have 5 different slots, so that represents each position. So for example, A here in this instance is slot 1. B is in slot 2. C is in slot 3. D is in slot 4. And E is in slot 5. But they change around in this instance, and this instance, and this instance, because A goes into slot 5 in here, and B goes into slot 5 in here. So these are examples of different combinations. But we're not actually looking to make 120 different boxes with every single outcome. That wouldn't be a very smart way of evaluating permutation. The way we would look at this is, well, in the first slot, judging by the fact that we can only use each letter once, we can't just use A as a combination, we have to realize that there are only 5 different things that could go in slot A, because there are only 5 letters that we start off with. Well, let's say then, after writing this list down, that A has been used in slot 1. In slot 2, we now have 4 different things we can use. So we put 4 in here. So let's say that was E that was used. Now we only have 3 for slot 3. And let's say C is used, then we have 2 for slot 4. And in slot 5, obviously, the last one will go in. So we can say this is 5 times 4 times 3 times 2 times 1, or 5 factorial, or 120 different outcomes for this instance. The thing is, that's only one example of how permutations are used, because it's not always going to be the factorial of the number of values in there. The reason being, there might be not all values might be used when creating a different arrangement. So for example, we might have a password, right? And you get to choose from all the digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. And let's say we want to create a 6-digit combination. 4, 5, 6. So we've got 1, 2, 3, 4, 5, 6 different boxes. So the way we would write this is NPR, obviously, as we've just learned. And N is the number of different values that we can choose from, which in this case is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different values. So N is 10. But the thing is, we're not choosing all 10 because all 10 can't fit into the 6-digit combination here. We're only choosing 1, 2, 3, 4, 5, 6 different things. So R is 6. So the way we can write it is 10p6. So the total number of values we have is 10p6. So let's think about this using this diagram we have here. How can we arrange them and find the total number of possibilities? Well, in the first one, we have all digits accessible to us. So we have 10 different combinations that can fit into slot 1. Also do remember that we only have 6 different slots, but that doesn't mean we can use every letter in every single one of them. Let's say the combination needs to have unique letters. So let's say if we use 0, for example, we can't use it again. If we use it in slot 1, we can't use it again in all the rest. So now we have 10 different possibilities, right, from all these different digits here. So let's say 0 is used. Now for slot 2, we only have 9 left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that we'll write 9 here. Let's say if digit 4 is used, that means that we have 8 left for slot 3, 7 for slot 4, 6 for slot 5, and 5 for slot 6, as we keep using up different digits like that. That means that the total number of combinations is 10 times 9 times 8 times 7 times 6 times 5, which is not 10 factorial, because then that would include times 4 times 3 times 2 times 1. That's why it's not always factorial. If N and R here, if they're both the same, then that means that it'll be factorial. But in this case, the R restricts how many times you go down. So you go down 1, 2, 3, 4, 5, but also 6 times. So there are 6 different things you multiply together, not 10. So that means our total number of combinations is, we can use our calculator to do this. So if you have the green TI30XB calculator, you can use permutations in order to calculate things without having to use this diagram that I've drawn here. So you can write 10, and then you press the PRB button at the top left of the calculator. And then press 1, because that's NPR, as we can see, and press 6, and then press enter, which gives us 151200, which is essentially just the same as this multiplied together. So yeah, that's our next example of permutations. In the next video, we'll cover more about permutation questions practice, because there are some much harder questions that may come up on an AdMath paper. But for now, let's move to combinations. So let's move on to the other strand of probability. So we first covered permutations, but other than permutations, there's also combinations, which is also equally important. So while permutations is the order of things, for example, if you have A, B, and C, it can also be looked at C, A, and B, or C, B, A, or B, A, C. For combinations, if you have A, B, and C, the order does not matter. So there's only A, B, and C. It could be B, C, and A, but these two in combinations are viewed as the same thing. So let's start from the beginning. What is combinations? It's actually like the values that it's the values that you choose rather than the order in which you choose the values, unlike permutations. So let's take an example. Let's say you have 22 kids in a class and 5 are going to be chosen to be representatives of like class leaders, for example. Well, we could say that the 5 people are persons A, B, C, D, and E. But the thing is, it doesn't matter if we pick person A, then person B, then person C, then person D, then person E, or if we pick person E first, and then person B, and then person C, and then person D, and then person A, because they're all viewed as the same thing. Why is this? Well, if you think about it, they're all doing the same job, right? They're all being the class leader. It's not like there's a hierarchy. One of them is not going to be like the main leader, and then another is going to be like the secondary leader. They're all leaders. It doesn't matter which order we choose them in because it's all the same thing, essentially. We can think of this another way. Let's say we have, we have 3 white marbles and 4 black marbles. So let's say we're picking the 4 black marbles. It doesn't matter if you pick this marble first and then this marble and then this marble and then this marble, or if we do it the other way around, because ultimately the marbles are the same things. It's just how many or which ones we choose. So in this thing, it would be viewed as seven things, and you're choosing 4 of them. So we can just look at it as NCR, whereas permutations is NPR, combinations is NCR. Logically speaking, permutations will always have more values because you can always rearrange the way that things are arranged. However, in combinations, there's no need to rearrange anything because they're the same thing. It doesn't matter if you pick this, then this, then this, then this, then this, or if you pick E, then C, then D, then B, then A, because it's just about which values you're choosing rather than their arrangement. So let's take our example of 22 children and 5 people who are going to be chosen as class representatives. There's actually a specific combinations formula that we do get in add math, which is n factorial over n minus r factorial r factorial. And if we remember, factorial is all the things before it multiplied by it times the thing itself. For example, 3 factorial is equal to 3 times 2 times 1. 10 factorial equals 10 times 9 times 8 times 7, so on and so forth until times 1. So let's take this example again. We have 22 people and 5 of them are going to be class leaders. So if you use this formula, then it's 22 factorial over 22 minus 5 factorial 5 factorial, which is the same thing as 22 factorial over 17 factorial 5 factorial. Well, this looks like it'll be very long because 22 factorial, if we remember, is 22 times 21 times 20 all the way until times 1, which is quite a big number. There is, however, the calculator which we can use to calculate this, because otherwise it would take a very long time. So the calculator, we can do 22, and then we click the PRB thing that we had referenced earlier on our green calculator, and then we click the 2 instead because it's NCR as we see on the screen that comes up. And then we click 5. And what our answer is 26334. So 22C5 equals 26334, which is essentially the same thing as this. So now we've gotten a basic idea of what combinations are. It's basically not about the arrangement as it is here, because this is equal to this in combination terms, as the arrangement does not actually matter. ABC is the same as BCA, because what matters is actually the values you take instead. So this is a basic idea of how permutations and combinations work. We'll go over into some more complicated practice questions on them both in the next video, and also we'll go over their one final use, which is in the binomial theorem, which is something very important. But other than that, for now, let's just wrap up this video. Thanks so much for watching.